Hello and welcome to lesson 3.3, graphs of primary, reciprocal, and transform trig functions. So just recently we discussed or examined how radian measure is a better alternative to actually using degree measure, and that pi radians is equal to 180 degrees. Well, we're going to use this today to actually graph sine, cosine, tangent, and also cosecant, secant, and cotangent functions, and realize how to actually look at them. Now, first of all, I just want to remind you that the function cosecant of x is the reciprocal of 1 over sine of x. And this does not equal sine inverse of x. These are two different functions. Sine inverse of x is sometimes also called arcsine. Likewise, secant of x is the reciprocal of cosine of x, which is again not equal to cosine inverse of x, or sometimes called arc cosine. And last but not least, cotangent of x is the reciprocal of tan x, which is again not equal to tan inverse of x, or sometimes also called arctangent of x. So just some things to remember before we continue on. Okay, so these functions are going to look exactly the same they did in radian and degree measure as they do in radian measure. Just remember that we're looking at degrees. So some key points of sine. Sine of x goes through the point 0, 0, pi over 2 and 1, pi and 0, 3 pi over 2 and negative 1, and 2 pi. It's all based on a circular pattern, so it gives you a semicircular kind of motion as you go through these curves. What we do is we copy this same shape when we extend our graph. And as you can see, this function has a period of 2 pi. Now, using what we know about reciprocal functions have vertical asymptotes when the original function is 0, vertical asymptotes at multiples of pi units, which I'm drawing in here as dashed lines. They also intersect when the functions, both functions, are equal to 1 or negative 1. They approach these vertical asymptotes. It doesn't actually have a horizontal asymptote, but again, wherever our reciprocal function is positive, the original function is positive, and vice versa. So we get shapes something like this. And so this red graph that I've now drawn is y equals cosecant of x, or at least a good sketch of it. Now remember, sine and cosine are just 90-degree translations of each other. So cosine usually starts at the point 0, 1, has a 0 at pi over 2 and 0, has a minimum of pi and negative 1, comes back up to 0 at 3 pi over 2, and has a maximum again at 2 pi. Again, we're going to copy the shape on the other side and extend and make it look semicircular in nature. So make sure you're drawing curves here, not straight lines. So this blue function that I've drawn here is an example of y equals cosine of x. Again, looks very similar to what you've seen before. Okay, so vertical asymptotes again occur where cosine of x is equal to 0. And again, the functions intersect where you have y values of 1 and negative 1. And they get close to these vertical asymptotes, and again are positive when the function's positive, or negative when the function's negative. And as you could probably guess, secant of x is just a translation horizontally of y equals cosecant of x. And there we go. Okay, so last one, tangent of x. Tangent of x is actually a rational function of sine x over cosine x. So realize that tan x is equal to actually sine of x over cosine of x. That means the zeros of sine of x are the zeros of tan of x. Where cosine x is equal to 0 is where we get vertical asymptotes. Now, if sine x and cos x are equal to each other, you're going to get a value of 1. This only occurs at values of like pi over 4, or even 5 pi over 4. And as you can probably guess, add multiples of pi from there. They're also equal to each other, but negative, so one could be positive, one could be negative, at values of like negative pi over 4 and 3 pi over 4. And as you can probably guess, also multiples of, from that, of pi units. So again, we've got to go through these points and get close to these vertical asymptotes. So this function you may not have seen before. This is the function y equals tan of x. So again, we can find the reciprocal of this function. So to find the reciprocal of this function, the zeros will create vertical asymptotes. Where these functions are negative 1, where y equals negative 1, and where y equals 1, we have points of intersection between our original function and our reciprocal. Well, if cotangent of x is the reciprocal of tan x, that means cotan x is equal to cosine x over sine x. And these occur to be 0 when cosine x is 0. So again, draw a function or functions that go through these points close to these vertical asymptotes. So this red function that I've drawn here is an example of cotangent of x. And again, you can see tan x and cotangent of x are periodic in nature. Now, part of our exploration of these things is to be able to create expressions to describe where the functions are having local maximums or local minimums, or where their vertical asymptotes occur, and so forth. So, remember cosecant of x is based off of sine of x. I'm going to draw a little sketch of sine x. And cosecant x looks something like this. Well, local maximums are these points that I'm highlighting in red. These are spots where the function reaches its highest possible point. Well, these points can actually be located. This is at a value of 3 pi over 2, and the first one is at a value of negative pi over 2. Well, you can see the distance between the two local maximums is actually pi units. And it's not too hard to see that if you continue this function, my apologies, they're 2 pi units away. It's not too hard to see that the next ones will again occur 2 pi units away. So to describe a function to represent where the local maximums occur, first realize the x values are real numbers. Those x values can be described in the form of a geometric sequence, arithmetic sequence. So we start with one of the starting values, one of their first local maximums, that occurs at negative pi over 2, and then we add multiples of 2 pi. And how you write a multiple of 2 pi is 2 pi, and you multiply it by a variable k, where k is an integer. And this is how you go about writing an expression to actually find where the local maximums occur. Now, if you want, you can simplify this piece, this negative pi over 2 plus 2 pi over k, by finding common denominators. You can even factor out the pi. To describe the expression. This isn't necessary, but it is an option. Okay, so what we shall also review is some of our skills with sketching transformations of functions. Now please remember that you should always place transformed functions in fully factored form. So I can factor out that 3 from the theta and the 3 pi. Well, what this tells me is we can use a transformation statement to actually graph this. So I can use theta and y using my transformation statement. I'm going to take my values of theta and I'm going to divide by 3, and I'm going to subtract the value of pi. And my y values, I'm going to multiply by -2, and I'm going to add 1. Now, because we're using multiples of theta being multiples of 3, so I would actually use our pi units, or pi over 2 units, as multiples of 3. So this is where I would put pi, and this is where I would put 2 pi. So I'm just going to extend on the other side. Our maximum values can go up to the values of 2 or -2 if it was a regular, 1 or -1 if it was a regular sine function, because of the vertical stretch, we've got it going up from -2 to 2, or even the fact that it's also been translated up 3 units, I'd actually use a maximum of 3 and a minimum of -3. Okay, so what we can do is we can draw our first graph of sine of x, if you wish. We can use those points that we get. Again, using them in radians. Radians are better. And finding where they change. Okay, so if I take this, I get negative pi and plus 1. If I do this, I get negative 5 pi over 6. -1. If I do this, I get -2 pi over 3 and 1. If I choose this one, I get negative pi over 2 and positive 3. And last but not least, negative pi over 3 and 1. So now I can draw my resulting graph where it may be. Negative 5 pi over 6 and -1 right there, right there. So I'm just drawing these points. And again, you can extend the graph if you wish by drawing the same pattern as you go. And again, try to make them circular in nature, or semicircular in nature. And there you get your transformed function. Okay, let's try that again with another expression. Okay, so again, factor. Write your transformation statement. Here we're taking values of theta and we're dividing by 2, and we're adding pi over 4. Here we're taking our y values and multiplying by 3 and subtracting 1. In this case, your value of pi is being divided in multiples of 4. So let's use pi as this, and 2 pi as this. Just so I can see it on my graph as well. Maximum values are going to be 4 and possibly -4. I need to get that from the 3 and the 1. So that's the scale I'll use for my y values. Okay. So now I draw cosine. Original drawing of cosine first. And use those points to figure out my new locations for my new function. Okay, so it's just a matter of substituting in. You can check these values with your calculator if you like, or you can just work these out using your own brain. And now draw your new locations. And again, if you'd like, copy your items. Extend your graph. Try to make them semicircular in nature. It's very difficult when it's stretched like this. And there we go. Thus concludes this lesson.